Okay, so I'm going to go over the basic idea and what we call the canonical use cases, which are basically what are the sort of the typical scenarios that we're targeting. Then I'm going to go over how you access things that are in the GFFS, then how you put things into the GFFS, and where we are on deployment. So the basic idea is really simple. We're going to take resources, and I'll define that term a little bit more clearly in just a second, and map them into a global directory structure. So this is a directory structure like you're completely used to from your everyday life. It's path names, basically. Then we're going to take that global directory structure and map it into the local file system as a local operating system, as a file system, so that I can now access those resources remotely and have the underlying system take care of caching, prefetching, security, all that kind of groovy stuff. So this picture is trying to sort of show that we can map in data resources, or in fact processing resources or applications, whatever we want to map in. That's the basic idea, and we imagine this sort of being used in three typical ways, particularly in campus bridging. So first, let me define what I mean by a resource. A resource to us can be lots of different things. It can be a compute resource like the Blacklight queue. It could be a compute resource such as a metascheduler or a queue of queues that might schedule jobs around the system. A job is a resource. It's running. You can interact with the job through the grid file, global file system. It can be obviously data, files and directories, directory structures that you have, instrument data that's lying on an instrument somewhere. It can be identities such as groups and things like that, and the list sort of goes on. And what we mean by access is we can either create things, we can read them, we can update them or write them and delete them. So basically we have what's sometimes called CRUD, access to these resources that are out there. And so creating a file is pretty obvious. You create a new file, it shows up, you can write to it, that makes sense. For some other resource types, you have to think a little bit, and we've defined what it means. If I want to create something new in a compute resource, well, I might be creating a new job by copying a file that defines the job into a compute resource. So this sort of goes on and on. So there's sort of three, as I said, canonical use cases, and they're sort of in some ways trivial, but they sort of highlight it. The first is I'm on a campus, like I am right now, for example, and I want to access a resource that's at one of the SPs, at one of the centers. So that could mean I want to access maybe my home file system at the center. I may want to access the queues at the center. I might want to do something at one of the centers. Similarly, from a center or from a running job, I might want to access a campus resource. So at the center, let's suppose that I'm shelled onto one of the machines there on a head node, I might want to be able to do a make and a compile that in fact is going to get the sources off of my machine back home. Or alternatively, I might have some shell scripts that I want to run that actually are physically at home. Or I might want to incorporate data that came off an instrument back at home and access that either from the shell or get it staged into a running job. So that's getting to campus resources from the center. And then finally, accessing campus resources from another campus. So the GFFS isn't just about center-center interactions or campus-center interactions, but really about building an environment where we can have campus-campus interactions where people can map their resources into this shared namespace and then access them subject to the access control policy that they've decided to have in place. So, for example, in a campus-campus sharing, we might be sharing some instrument data or some file system information between two collaborators or three collaborators or 20 collaborators. Or we could, in fact, each be sharing clusters. I could have a couple clusters on my campus and somebody else could have some on theirs. And we've decided that we want to work together, and so we're going to create a shared queue just for our jobs that will then schedule jobs between our respective clusters. So there's all kinds of resources we're going to use the GFFS to get to. So how do we get to these resources once they're in there? So there's basically three ways to get to resources in the GFFS. The first one is we're going to mount the GFFS in a local file system, and that's the one I'm going to describe first. The second is through a command line client, and then the third is through a GUI. And I'm going to spend pretty much all the time talking about the file system mount. So the basic idea is we have this global directory structure. It looks like every file system you've ever seen in your life. And what we're going to do is use something called Fuse, which stands for File System and User Space. And we have a grid-aware Fuse driver that will take this file system space and map it into the local operating system at some mount point that you specify. So what this means once we do this is exceed resources that are in the GFFS can be accessed in a location-independent manner. So we can access files and directories that are remote. We can access programs that are remote. We can access shell scripts, anything like that. In fact, our shell scripts that, if I'm at a campus, for example, I can run shell scripts that or programs that operate on data in the GFFS, whether it's data that happens to be locally, happens to be at Pittsburgh or TAC, or happens to be at a collaborators institute, let's say at University of Colorado. And the application doesn't have to be modified in any way. This is really the beauty of the GFFS and the Fuse driver, is we don't have to change our way of doing things. We can still have shell scripts that recursively descend through directory structures, looking through things. We can have them just operate on data that's there. It's all just sort of part of, just like any other file system. Similarly, we can start jobs by copying job description files into directories that represent compute resources. We can, a running job is also a directory, so we can CD, so to speak, into a running job, and there's a file that's called its status, which we can cat out to see what the job is up to. There's a subdirectory in the job directory called the working directory, and if I CD into that, I'm actually in the session directory of the running job, wherever it happens to be, and I can copy files in and out, or I can cat files to see what's going on. And I don't need to know where any of this stuff is. So that's the basic idea of what we're trying to provide people, is a different access paradigm. Instead of having to explicitly manage moving data around between places, you just use the data, access the data, and we take care of the underlying issues. It's very simple to start. In fact, I'm going to show you this in a second. You just need a directory that you're going to mount it into, just like you would with any directory mount. And then you do a Fuse mount of that directory, and you have it. And we'll see that in just a second. So I got to see what time it is. 16, so I got 6 minutes. Okay, so this is an example from a running job. I decided to capture this ahead of time, as opposed to try to get some jobs that would actually be running while I was doing this. In this particular case, I've done I'm in a directory called grid queue, which is this global queue. And then under that, there's a subdirectory called jobs, and under that, there's a subdirectory called mine. And so whenever I do a directory listing on jobs mine, it's only going to show me my jobs. And I can furthermore divide it into running, queued, or finished. So I've done an LS here, as you can see, on my running jobs at that instant in time. And those are the job tickets. You can think of those as essentially equivalent to any job ticket you get from a queuing system. And I can LS inside of that job, look at the activity working directory, and see the files. This is somebody I'm trying to remember what this person's job is doing. It doesn't really matter. They're running some application, and you can look at what their current R usage is. You can look at the programs that they've copied in and out and they've generated, and so on. So the whole idea is to use this one paradigm, the file system, as a means to not only interact with data that people have at other places, but also running jobs, policies, all kinds of things, using essentially scripting technology. So what I'm going to do next is I'm going to show you how this works. It's really very straightforward. At this point, you should see a standard Unix shell that happens to be my home directory. I'm going to use grid instead of exceed, and right now you can see there's nothing in grid. It's not mounted. There's nothing there. It's just a standard Unix directory. let me just see if we can get it there. Just a standard empty Unix directory. Now all I have to do in order to, I'm going to no-hup it because that's what I always do. Now I've already authenticated into the grid using my Exceed portal login identity. Exceed grid fuse mount. I have to say local grid. Pop that baby in the background. And now if I do an ls on grid, first time it takes a second because it's got to get stuff in. I've mounted this global namespace, and I can cd into grid, home, Grimshaw. It's just a regular Unix directory structure at this point. I have no idea, I don't need to know, rather, where any of these files or directories are located. Some of these directories, in fact, are on PC in my office. Some happen to be on a server in the computer science department somewhere. They could be anywhere out there. You can just do whatever you want with them and do that. So, for example, if I go into, I think it's Picture Converter. We have a little program in Picture Converter. It's a shell script, which basically, when you run it, it goes into a target directory that you, source directory, and for every file in there, it runs a program and generates a file and another thing. It's a pretty typical kind of thing that you might want to do. And this program knows nothing about the grid or anything about it. So if I go back up, I don't want to get into too long of an explanation of this because I have to find the target source image. Clean out target images star. Geez, I don't want to do this. My Unix skills are, I want to say bin rm. Just get them to go. So it's going to dump them all out. All I'm going to really do now is I'm basically going to say Picture Converter. Oops, where am I? Source, target. Okay, so what this is going to do is what you would expect. It's basically going to go out. Well, I typed in something wrong somewhere, so I'll deal with that later. I don't remember the command line parameters. The point is you don't need to know where any of the stuff is out there. That's the main point of this exercise. So what I want to do, so that's mounting it in. It's pretty straightforward. You can also get to it through command line tools if you're into scripting and you don't have the ability to do a fuse mount in a particular environment. You don't have permission to do a fuse mount or something like that. So you can do copies, back and forth, remove, all the usual stuff you would expect. There's also a client tool, which basically is a GUI way of doing the same thing. It has a shell associated with it that knows about tab completion and all that. And this is where you can also export data and things like that. You can start jobs here. The other thing that the client allows you to do is make associations between file system types and programs. So, for example, a .docx file can be associated with Word, or if you're on Windows, or I can't remember the Star Office equivalent. So if you double-click on one of those types in here, it will essentially open that file out of the GFFS and let you work on it. The final way that, and this includes also the ability to set permissions and stuff like that, and I don't have time to go into the security model, but the basic security model is access control lists for read, write, and execute on each type of thing that you want to have. So that's sort of the that aspect, the accessing part in a nutshell. Attaching and provisioning is really pretty straightforward. Suppose we have a user, Sarah, and she has data on a department file server, on an instrument in her lab, and maybe a TAC. She can choose to export into the global namespace different subdirectories on those different places at a path that she specified. Just like, I don't know if you guys noticed earlier, I had some directories from my local PC mapped in, and now she can either access those from anywhere using the GFFS, but she can also set up access control so a colleague of hers at another institution could get at one of those things through the GFFS without having to obviously log into her machine or get an account on her machine or anything like that. And the important thing is Sarah controls the access control policy to her data. Okay, not exceed administrators, but Sarah at her institution is going to control that. The way that you do it is you run a tool called export. There's also a GUI equivalent of this, but with this audience, I thought the command line version would probably make more sense. You specify the server that you're going to be doing the export from. In this case, it's containers, big state use, Sarah server. The path on that server, development sources, for example, and the path she wants to link it into in the GFFS, home Sarah dev. You can also export Windows shares and directory structures via SSH if that's what's the way you have to get to things. It's slow, but it's sort of like SSHFX. So this allows us to take Windows data, all kinds of stuff, and map it into the global namespace. I think I'm beginning to run out of time. Is that right, Sergio? Yes, I have a minute or two left.
Maybe if you wrap up in 2-3 minutes.
Last slide. So basically, I've talked about the canonical use cases, how you get to data, and how you get data into the GFFS. The third thing is, where are we right now? If you want to be able to export data, you have to have a Genesis 2 container. If it's a compute resource, you can also have a Unicore 6 container if you're mapping out a queue. There's an installer that's been developed for the GFFS package for the service providers and a campus bridging installer. And this is both client side and the server side, and there's training materials. And that is a GFFS in a nutshell. I would love to figure out what mistake I made in my in passing in commands. But anyway, it doesn't matter. I don't know why that didn't work. Anyway.
Well, okay.
So that's where we are. Questions?
Yep, questions.
Andrew, how did you specify which directories were to be mounted when you did the fuse mount?
So when you do the fuse mount, it mounts the entire GFFS namespace into that mount point. I believe there's a way to specify a particular subdirectory to start as the mount point. I never do that, so I'm not sure how to do that. But basically, the default behavior is when you mount it to a local directory, it mounts the entire GFFS tree at that point.
Okay, and if you wanted to put something, if you wanted that mount to include something from your local campus, you would previously have used the export?
Exactly. You would have done an export, and the requirement is that we have a Genesis 2 container, which is the same way of saying it's a service, that can see the file system that you want to be able to export, so you have to be running there. We found on campuses in particular, oftentimes in many departments, users they may have a Windows machine, which is fine, we can run on a Windows machine, but they oftentimes have really bad Windows machines. And so what we do in that case is we do what we call a file system proxy for a Windows share, and it's just it doesn't soak up so much cycles on their machine.
Okay.
So Andrew, this is Phil Blood at PSC. So a user could have any number of GFFS namespaces to which they could export files?
Yeah, I mean basically you can export as many subdirectories as you want to from as many different places, and you're just putting them into the namespace somewhere. It's just like doing it's similar to basically doing a mount. You're basically saying, here's a path in the GFFS that when somebody goes to this path, I want them instead to end up going to this other file system somewhere.
Okay, so users on Exceed could have any number of these that they could use for different purposes, or?
Certainly they could. Now, at the SPs, the intention is that initially we will bring it up so that only certain restricted file systems at the SPs are going to be have it so that users can export their stuff from there. That's a policy decision which file systems to make available that the service providers will decide. But if a user downloads the campus bridging package, they can export whatever file system they want. It's their data.
Right. I guess I'm just thinking of, and this is the first time I've looked at this, but you define a namespace, right, where you want to export those any certain set of directories, right?
Right. We have Exceed will be defining that namespace.
Oh, so there will be just one namespace for
Yeah.
Exceed. Anything you export will go to that.
Right, and so that way you can use the same path from anywhere to get to the same set of stuff.
And then if you want to change which people can access which portions of that, you can control that.
You can change the access control on the tree, essentially.
Gotcha. Okay.
Yeah, it's really modeled very heavily on Unix and Plan 9 and systems like that. We're trying to make it as obvious to people who are familiar with Unix as possible.
Andrew, for people who want to access the Exceed namespace, do they need to have an Exceed account?
Well, so that's a really good question. Certainly in the beta, that's the intention. But a person can map data into the namespace. Say for my institution, or a user, Sarah, wants to map some stuff from her campus in. She can decide who is going to have the ability to get to that data, and she can set access control herself. That's her policy decision. So really, it boils down to what policies people are going to, what the access control they're going to allow on their individual things. You can either choose to use an Exceed credential as part of your access control policy, but the model doesn't say that people can't create their own identity services and use those in the access control list if they want. So I know that's not maybe the kind of answer you would want. I mean, the basic answer is it depends on what the user decides to do. But certainly in the beta, to access Exceed resources, that's what we're going to be expecting, is that people have a portal account.
And Andrew, you say that obviously there will be ample documentation that will be provided along.
Documentation is our weak point right now, and that's one of the things we're working on.
Okay, but when deployment is declared by Exceed, then of course there will be ample documentation available and things like that.
Yes, there's only a few basic things you can do. It's just you can combine them in lots of different ways to meet different use cases.
Andrew, what is latency like?
Well, the typical computer answer, right? It depends. So first off, I think I'm getting over my time, but I'm happy to answer this. Latency depends a lot on how close the resource is. So latency on grounds, that's what we call campus here at UVA, is really pretty good. When it gets further out, it takes a long time to establish an SSL connection from Virginia to California, for example. So that's one of the reasons why we do a lot of caching and cache and validation work, so that every time you touch something, you're not going out to the network, because that will kill you. So small metadata operations are much slower than a local Unix system. So if you're creating 1,000 files, it's going to take longer. This is a problem with a lot of large-scale distributed file systems. Is the metadata operations tend to be slow. Bulk data transfer, the bandwidth is pretty good, but the metadata is slow.
Okay, one more question before we let Andrew go, and then you all know where to find him. So,
So, Andrew, this is Ralph.
Hey, Ralph.
So, when you export a